Hello again. Let me begin this lecture with a summary of the previous video. The main purpose was to understand how we could interpret the elements of in an algebraic function field in the sense of evaluation at given point or the rational places, or in general given a place at a given place. We still don't know if there exists a rational place, so degree 1 place in all algebraic function fields, but at least if the ground field K is algebraically closed, since this extension degree is finite, the residue class field is an algebraic extension over K. And if K is algebraically closed, this extension degree will be 1. And we can conclude that all places are rational, and we can view the elements in the function field as a function. But still, now the question is that we still don't know degree 1 places exist, because we still don't know do we have a place in an algebraic function field. So the set of places non-empty. And the next theorem will give a positive answer for this question. As usual, f over k denote a function field. And to see that evaluation ring or a place exists, we consider a subring of f containing k. This subring, such a subring, always exists. And we suppose that I is a proper ideal of I. Then there exists a place which contains the given proper ideal I and the ring OP. And the given and the corresponding valuation ring, contains the given ring R. And to prove this theorem, actually we will show that such a valuation ring exists depending on I, and then we will see that the corresponding place containing I, and we will prove it by axiom of choice. And for this purpose, we consider the inductively ordered set, and then we are able to choose a maximal element from this set. More explicitly, let me define the curly F that contains subrings of F with these two properties. So that means they will contain the given R and the ideal IS. Here recall that it is defined as follows. That means they contains the finite sums of the products of elements AV from the given ideal I and the elements SV from S. As an exercise, we can see that this set indeed is an ideal in S, given ring S. And here we consider the subrings such that this ideal is proper ideal in S. So first, let me observe that this curly F, this set is non-empty, because if this we know that there exists a subring R, and we consider its proper subring. It satisfies these two properties. So R is in the curly F. And now we want to show that this is inductively ordered set by inclusion. In other words, it is inductively ordered set by inclusion, or equivalently we will say that we will show that if Si with an index like omega is a chain in curly F with respect to inclusion, so that means Si, the ring Si is contained in Sj for when I is less than J. So we consider here the index set as ordered. And if we are able to show that the union of Si over omega is also element in curly F, then we can conclude that F is inductively ordered set by inclusion. And in order to see that this union is in curly F, first we need to see that S prime is a subring of F. Sorry for the mess. And it should contain R, and the ideal Is prime is a proper ideal of S prime. To see that S prime is a subring of F, we consider two elements in S prime, and we want to see that there's summation and the product also in S prime. So in this case, when we consider these two elements, if it is in the union, we can say that there exists ring Si and Sj that contains the elements X and Y. They are not supposed to be same, but since we consider inductively ordered set, without loss of generality, if I is less than J, we know that the ring Si is included in Sj. In this case, we can view X as an A, we can view X as an element in Sj. And since this is a chain in F, Sj is a subring of F. And it shows that summation and multiplication also in Sj, consequently in S prime. And this shows that S prime is a subring. And similarly, since we consider the chain in F, all contains all contains the given ring R, so R obviously a subset of S prime. And finally, we want to see that IS prime is a proper ideal of S prime. We prove it by contradiction, and we suppose IS prime is equal to S prime. So that means if we have this equality, we can write the unit of this ring, which is 1, as a combination, as a finite sum, or as an element from this ideal. Here AVs are chosen from I, and the SVs are from S prime. So for this SV, since it lies in S prime, we know that there exists the index J0 such that, and since this is a chain with respect to inclusion, there exists like a bound for this index set such that these all SVs, finitely many SVs, lies in Sj0. But this shows us this finite sum indeed can be seen as an element in the ideal ISJ0, which is indeed in purely F. So that means this is a proper ideal of Sj0, but this gives us contradiction because we find the unit in the ideal. So that means we can get this inequality. So we may conclude that IS prime is a proper ideal of S prime, and this shows that S prime is also in purely F. And by applying Zorn's lemma, when we have an inductively ordered set, we can claim that there exists a maximal element in F, maximal in the sense that this is a subring, maximal subring that contains R, and the ideal IO is a proper ideal of O. Okay, so actually this shows also us the existence of a valuation ring that contains the given R and depending on the I. And if we are able to show that this is a valuation ring, we will be done. So now our claim is that such a ring is a valuation ring. And in order to show that, we consider the first definition, its abstract definition. Our claim is to say that for any function, z in O or its inverse in O. And we prove it by contradiction. And let me suppose that neither z, so there exists z in F such that neither z nor its inverse in